Alright, we are live again. In case anyone's watching, in reverse, going back to the start of I guess I could call it a series, and trying to see where we left off. At the end of the last stream, I was, I was copying from this other video, but I didn't really understand what was going on, so I went and did some research of my own and found this good article over here, or blog post, that actually explains the math very well. I was having some trouble understanding the actual derivations, and why we're trying to match the trying to find why we're trying to approximate the noise itself, the epsilon theta, and what these terms exactly inside were. But I'm probably gonna review this. I read this a couple hours ago. Anyways, I'm gonna have some stuff to do really quick. Some trouble understanding the. All right. Why is I'm trying to share this live stream on a Discord server, but saying playback on other websites has been disabled by the video owner. I have not disabled anything. Okay, I think I got it. There you go. Alright, so I shared it there. Now, there's some other servers I could share. Hold on. Oh, actually, I think it's a different server. Hold on. All right. I need to reread this. All right. All right, so over here they don't derive elbow. I've watched some videos on the derivation, but I mean, I guess without a foundation in statistics, it'll be quite difficult to understand, but I don't mind. This is not too much abstraction. Just saying that these terms over here is less than or equal to the log probability of x. So we're taking the expectation along q of x1 given x0 for the log of p theta for x0 given x1. So in other words, we're weighing for the probability of x1 given x0, and with that x1 we're then checking what our probability from that x1 is of getting back x0 with our p theta, with our approximized q function. Alright, that makes sense. Then we're taking the KL divergence of q xt given x0 and p of xt, which if I remember correctly, I think they're going to say it over here. Yeah, this entire term has no trainable parameters, so it's ignored during training. And the third term, this is the important one, if I remember correctly, or the most important one, is to formulate the difference between the desired denoising steps, p theta of xt minus 1 given xt, and the approximated ones, q of xt minus 1 given xt, or conditioned on xt and x0. Why again do we need x0 over here? I mean, if we have xt, shouldn't we be able to get xt minus 1? Or, I guess, in other words, couldn't we just immediately go by getting q of xt minus 1, keeping that in memory, then getting q of xt? But it looks like what they do is you get some q of xt, some noise q of xt, and then given that and x0, they then generate a new xt minus 1. Actually, might as well ask, why do we, what's it called? What's I gonna look up? Here, let me just copy this. In diffusion, actually, why don't I just copy the whole paragraph? I'm reading a diffusion blog post. Here is an excerpt. Why do we take q of xt minus 1 given xt x0 rather than initially get xt minus 1, store it in memory, apply a diffusion step on it, then check for actually q of xt minus 1, is that it's not a probability distribution. No, it's a real number, right? And I guess I could make it more efficient. Okay, no, DKL, yeah, that's to compare two probability distributions, or not necessarily probability, two distributions. So there's a distribution of xt minus 1. Q of xt given x0. Okay. You know what, let me read this from the start. There's so much. Okay. X0 gradually Gaussian noise. So given a data point x0 sampled from the real data distribution q of x, x0 sampled from q of x, one can define a forward diffusion process by adding noise. Specifically, at each time step of the Markov chain, we add Gaussian noise with variance bt beta t to xt minus 1, producing a new latent variable xt with distribution q of xt given xt minus 1. This diffusion process can be formulated as follows. Q of xt given xt minus 1 equals the normal xt given mu t, the mean, equal to the root of 1 minus beta times xt minus 1. Yeah. And variance or covariance equal to beta times the identity matrix. So there's no covariance. Square root of 1 minus bt. When bt is 0, that means that we are taking the entire xt as a mean. All right, and as bt increases, we shift. I don't know if I'd call it a weighted average, but we get closer to 0. So it would be 1 minus 1. Yeah, we're ending up closer to a mean towards 0. Okay, since we're in the same standard deviation, note that q of xt given xt minus 1 is still a normal distribution defined by the mean mu and the variation sigma, where mu t equals root of 1 minus bt xt minus 1. Okay. So you can go in closed form, x0 to xt in a tractable way. Mathematically, this posterior probability minus q of x1 to xt given x0 is the what's it called? Is the pi loop or product of q of xt given xt minus 1 from t equals 1 to t. The symbol colon in x1 to t states that we apply q repeatedly from time step 1 to t. It's also called trajectory. So far, so good. Okay. For time steps t equals 500 is less than t. We need to apply q 500 times in order to, reparameterization trick. We define alpha t as 1 minus beta, alpha bar as the cumulative sum of alpha from from 0 to t, where epsilon 0 to epsilon t minus 1 is where all epsilons is sampled from a normal distribution with a mean of 0 and a variance of 1. One can use the reparameterization trick in a recursive manner to prove that xt is 1 minus alpha, and then you could replace it with alpha bar. So that means they could calculate xt immediately. So xt sampled from q of xt given x0 equals the normal with a mean of alpha bar t, or the root of alpha bar t times x0, and 1 minus alpha bar t times the identity matrix. Let me check something real quick. Oops. All right. The variance parameter beta can be fixed to a constant, chosen as a schedule over the t time steps. All right. Yeah, I already know this. Distribution as t goes towards infinity, the latent xt is nearly an isotropic Gaussian distribution. Therefore, if we right, if we reverse the q of xt, sample xt from yeah, so this is a probability distribution over, I guess, pixels, you could say, pixel values. And you sample xt minus 1 from this distribution. So we approximate q, okay. Since q of xt minus 1. Q of xt minus 1 will also be Gaussian for a small enough beta. Why is q of xt minus 1? I remember seeing a video which kind of explained this, but I kind of forget. So yeah, if our variance is low enough, yeah, well I guess since BT is so small, our variance is that makes our variance super low. And if our variance is super low, then it's not as affected as I don't know if I would say prior or posterior, but the before probabilities in the forward diffusion. So you know what? Let me put that in Paint. So I can understand. It's not like anyone's watching, but still. So let's say we have some data first, or let's say that this is the real. I guess I shouldn't do that. Let's say this is the real data distribution. You know what? I don't even need that other line. This is the real data distribution, right? If we had originally sampled our xt to be this number right here, okay, this is our x0, let's say x0. If we have a large variance, okay, hold on, we add noise based off, so our noise is centered around this, right? Okay, hold on. hold on. I need to think about this. For each point, we take noise according to this, just as a Gaussian, right? Okay. Say we then we have this x0, and then say our x1 is right here. Or say our x1 is right over here. If we had a Gaussian, if we had a super wide Gaussian, so from this we have some distribution. Its mean is over there, and it could go all the way over here. Then from x1, so this is x1, right? From x1. And this is our probability over here of getting to, this is, I guess we could say q of x1 given this specific x0. Okay. If we have this x1, if it has a very large variance, hold on, I need to think about this mentally. If we have this x1 over here, and we want to find what the most likely x0 was, then if we have a large spread, then I don't know, let's do this in yellow. All right. Well, it wouldn't be a Gaussian if I'm correct. Bro, this is just some mental gymnastics here. Hold on. Oh, hold on. Then we end up with some distribution which tells us from x1 what's our likely x0, right? So for now, I'll put it as a Gaussian, because it's more likely that a close distribution, or a close x0 had its mean and its the within one, let's say within one standard deviation. That's like the thickest part of the bell curve. If x1 is contained, that's likely to be x0. However, with a large enough variance, it won't exactly approximate this normal Gaussian, because we'll have these likelihoods of x0 to begin with. So if x0 is very likely, then it won't exactly be this yellow curve over here. It'll be, let's say, it might be something like this. This is like really likely. And then as you see, x1 starts to, the likelihood of x0 being down here starts to drop off, right? So it becomes less likely, right? Then maybe it picks up again, and eventually it drops off. So this isn't a normal distribution, but as you tighten that gap, if you make it very small, then the likelihood that hold on. Holy shit. Hold on. So this is x0 given x1. If you tighten the variance on x0, then x1 is somehow just normal Gaussian. Hold on, my light's turned off. Let me. Oh, let's turn on. All right. Okay. So if we have a small enough beta, then this will be super low, right? Let's say it's like that, and it won't be affected so much by these upswings in the base probability of x0, right? Like, so everything will be uniformly a bell curve. If everything is uniformly a bell curve, then like everything is. Man, this shit is confusing. if everything is equally a bell curve with no strange behaviors due to the likelihood of x0. Hold on. If everything. How do I redo? Okay, if everything is a bell curve, let's say this, and there's that. The likelihood of some x that's over here is also a bell curve. That's my understanding. So say I have a bunch this is difficult. All right. Do I have a viewer? No shot. If I have a viewer, say something. No, I don't think so. Okay, but back to this. All right, so I have some. You know what? Let me. So I pick, say, x0 to be here. I'm trying to find the probability that x0, or I'm trying to find the probability distribution over all x's that, I don't know, this is x1, let's say. So this is x1. I'm trying to find the probability distribution of all x's where x0 could have made x1. So what's the Q of x0 given x1? So that could be, if I have a very small, beta, I assume, well, that's what they say. They say that it would be a small, that would be a Gaussian, right? if it was a large beta, that would mean that very far away x zeros could have some probability of originating x1. So I assume that means that we wouldn't get an even Gaussian. So this could be like really high, very high probability, or maybe not very high. Some probability over here, right? And it drops off as the likelihood of x drops off. So let's say it's still getting closer to it. So it drops off. Let's say it picks up over here. Maybe stabilizes and then raises more, then drops off until, you know, finally it's something like that, right? Actually, it would tail off, not be straight. Let's say it was something like that. So that would not be a Gaussian, obviously. But if it was a small beta, then there's a very low likelihood that the further out x's, or the x's further from x1 could, you know, make x1, which is like a Gaussian where there's the tails, right? These tails are less likely than what's directly near it. And so that makes sense if we had a very small beta, because if we had a very large beta, say over here, this has some probability still, or say this would, okay, am I like retarded? This could have some probability of being what created x1, right? And so then we're being influenced by the likelihood of the x's themselves, while if the variance was super tight, let's use light blue, then we're not as immensely affected by the probability of the x itself. If I'm correct. I think I'm correct. All right, well that's my understanding. Choose p theta to be Gaussian and just parameterize the mean and variance. Okay. Rather than parameterize the entire distribution. If that would even be possible, I don't know how we would describe that. If we apply the reverse formula for all time steps, p theta x0 given xt, or x0 to t, also called trajectory, we can go from xt to the distribution. By additionally conditioning on time step t, it will learn to predict the Gaussian parameters, meaning the mean mu theta of xt and t, and the covariance matrix of sigma of xt and t for the hell? Chat rate. No one spoke in chat, right? Oh, I guess maybe the YouTube chat. Okay. By additionally conditioning times up. Okay. You can notice that the combination of Q and P is very similar to a variational autoencoder. We can optimize the negative log likelihood. After a series of calculations, we can write the evidence lower bound because the log likelihood is intractable. This is the expectation along Q of x1 given x0, and then the likelihood of x0 given x1, or log likelihood. then yeah, this doesn't matter. Yeah, this is backwards order before the third term, also referred to as LT. Formulate the difference between the desired denoising steps p theta of xt minus 1 xt given xt and the approximated ones q of xt minus 1 given xt and 0. Okay. It is evident that through the elbow, maximizing the likelihood boils down to learning the denoising steps LT. Important note, even though q of xt minus 1 given xt is intractable, well, if it was tractable, I mean, we might as well just use it. I guess unless it's a really huge function. I illustrated that additionally conditioning on x0 makes it tractable. Intuitively, a painter, our generative model, needs a reference image x0 to solely draw reverse diffusion steps. Thus, we can take a small step backwards, meaning from noise to generate an image, if and only if we have x0 as a reference. In other words, we could sample xt at noise level t conditioned on x0, since alpha t equals 1 minus beta and alpha bar equals cumulative sum of alpha. We can prove that q of xt minus 1 given xt and x0 equals the normal of xt minus 1 with mu tilde of xt given x0 of xt and x0 and b bar or b tilde p tilde or b beta tilde equals 1 minus alpha bar minus 1 alpha bar t minus 1 minus alpha bar t minus 1 over 1 minus alpha t times beta t. Alright, I don't quite understand how you got this term. I remember I found this earlier, but I forgot about it. Really quick, I'm gonna put some music. No copyright music. Or no copyright lo-fi, actually. Here it is.
You need to download Python to learn Python. You can learn right in your browser with hand.
All right. Q of xt minus 1 given xt and x0 equals normal of xt minus 1. Note that alpha t and alpha bar depend only on beta t, so they could be pre-computed. Okay, but what is this beta tilde? Or maybe I'm supposed to just take this for granted. You know what, I'll just take it for granted. So beta tilde equals 1 minus alpha bar t minus 1 divided by 1 minus alpha bar. Here, really quick, you know what? Q of xt. Where xt equals 1 minus alpha bar of x0 over 1 minus alpha bar. Wait, what was it again? Just beta t. 1 minus root of 1 minus alpha bar. No, xt, yeah, they use 1 minus alpha bar. Yeah, I guess this is some statistics knowledge that I don't have. Tells you how to come back to this. Anyways, so mu tilde of xt, yeah, x0 equals. All right, so this is some derivation that they don't give us, but I mean I'll take their word for it. Okay. This whole trick provides us with a fully tractable elbow, evidence lower bound. The above property has one more important side effect, as we already saw in the reparameterization trick. We can represent x0 as x0 equals, yeah, this we just took x0 equals 1 over the root of alpha bar t times quantity of xt minus 1, the root of 1 minus alpha bar t epsilon. Where epsilon is sampled from a normal distribution. By combining the last two equations, hold on. By combining the last two equations, each time step will now have a mean mu tilde, a target. What do you mean combining the last two equations? Mu tilde of xt equals, how did you just replace x0 with mu tilde of xt? What the fuck? I don't quite see how they. So this is the reparameterization trick, and they just isolated xt, right? Or x0. So xt equals that, and they put x0. So they put x0 in terms of xt. By combining the last two equations, each time step will now have a mean of mu tilde t, or target, that only depends on xt. Oh, this is two different equations. Whoops. Okay, mu tilde of xt equals 1 over the root of alpha of xt minus why did they put beta there? Or maybe what they did is they placed xt or x0 in there. They substituted x0 for this. Okay, I think that's what they did. They just substituted x0. Okay, I mean, I'm not gonna do the algebra. You know what? I'll do the algebra. So I have mu tilde of xt x0 equals root of alpha bar t minus 1 beta t over 1 minus alpha bar t. That would be times, oh, I don't really have enough space over here. You know what? I have to rewrite it. So this is, do I have a better pencil? Oh, actually, do I? Is this ass? I think I got it working. No. Fuck you. Alright. Q, or no, not Q. Mu tilde of xt, mu tilde t of xt x0 equals the root of alpha bar t minus 1 beta t over 1 minus alpha bar t, and then that would be times, you know what, I just write it differently. That would be times 1 over the root of alpha bar times yeah, okay, xt, well, I'd rather not write it in brackets. Times xt, bro. All right. Xt minus root of 1 minus alpha bar t times epsilon, and all that plus the root of alpha t times 1 minus alpha bar t minus 1 over 1 minus alpha bar t times xt. Okay, how do they go from this to that form over here? Well, I know that there's going to be 1 over alpha t. Alpha t or alpha t bar? Alpha t isn't mentioned anywhere, actually. No, there's 1 minus alpha t. How do they... Actually, I don't know. Well, they could do 1 minus... Am I gonna have to do some friggin' factorization over here? 1 minus alpha times 1 plus alpha. What does that give you again? I know that's some factorization. A squared minus b squared equals a plus b times a minus b. So that would become 1 minus alpha t squared. You know what? I'll just ask ChatGPT. Can you write the derivation I specifically want the derivation of mu tilde of xt using the found formulation of x0. I do not remember this. Alright, bro. Like, I'm looking for you to do the algebra. Maybe over here they explain the thing. I don't think they're gonna show it. Alright, so I'll take your word for it. Mu theta of mu epsilon of xt equals that. Yeah, and then mu theta, or mu t of xt is this. And then mu theta of xt and t is, okay, with epsilon theta. So we're only approximating the noise. Wait. But I'm kind of confused. This epsilon over here is just random, right? So why would this not give us the exact same thing if we had epsilon random? It doesn't have any unknowns here, except for like epsilon, but epsilon is stochastic anyways. Or is epsilon supposed to be an unknown? It's the epsilon that we sampled earlier. Oh, okay, I think I understand. So given that x0, this epsilon, which is samples from a normal distribution, is likely to be, you know, with x0 as the mean, is likely to range, you know, within some normal distribution, and we're trying to predict that normal distribution. And so what we'd expect is that the mean result of this epsilon theta would be the mean epsilon over, you know, enough time. All right. Kind of was gone for a bit. Okay. What was I again? Oh yeah. So we're approximating this this epsilon, which is sampled from a normal distribution with a mean around x0. If I'm correct. Because, yeah, we originally have xt equals... Wait. But don't we have that... Yeah, we have the mean over here, xt equals that of xt minus 1. So I don't really understand how... All right. I'm still kind of lost. Why exactly are we approximating epsilon? If epsilon is completely random, and it's not like... Yeah, this is just a normal between 0 and 1. It's not centered around xt. Did this shit just zoom in? Yes, it did. What the fuck? Alright. Is it like something like that? Like, I'm just trying to think of what hand movement I might have done to increase the zoom. Alright. Oh well. Oh. You know what? I'm gonna post my stream to Reddit. All right. back to this. So I don't understand why we're getting the epsilon. Why we're approximating epsilon? Why are we approximating a completely random variable? Why do we approximate epsilon if it's completely random? Oh, wait a minute. So we're learning the noise that we added, right? This epsilon over here. And if we just did xt plus that, then yeah, so we're essentially learning how to apply the noise, if I'm correct. X0 equals this. So we have mu of xt, x0, the mean of xt and x0. And that mean, if I'm correct, should be the original data point. It would be centered around that original data point. I think I'm starting to understand. I just need to check something. All right. Okay, so all right, we need to go back to this. Intuitively, a painter or generative model needs a reference image, x0, to slowly draw reverse diffusion steps. Okay. Thus, we can take a small step backwards, meaning from noise to generate an image. If only we have x0, if and only if we have x0 as a reference. In other words, we can sample xt at noise level t, conditioned on x0. This is too loud. Bro. Oh my god. There you go. If and only if we have x0 as a reference. In other words, we can sample xt at noise level t conditioned on x0, since alpha t equals 1 minus beta and alpha bar is cumulative sum. We can prove that q of xt beta, okay, and mu of xt given x0, and that mu of xt, that's supposed to be xt minus 1, right? If I'm correct. So q of xt minus 1, we usually pass, so we have an approximate, or not approximate, this is we're directly getting the mean of xt minus 1, instead of passing an xt minus 1, on its own. So shape provides us with a fully tractable elbow. The above property, hold on. The above property has one more important side effect, as we already saw in the reparameterization trick. We can represent x0 as x0 equals. Okay. By combining the last two equations, each time step will now have a mean mu t, our target, that only depends on xt. Okay. Right. So we're trying to find the noise added to xt minus 1. That got us xt. And it's centered, and that noise is centered around a normal distribution. Well, it's centered around mu tilde. And then with the reparameterization trick, we end up with it between 0 and 1, but it's still added to wait a minute. Yeah. It's mu tilde. Okay. Therefore, we can use a neural network to approximate epsilon and consequently the mean. So, okay, we're getting this mean, thus the loss function. Right. Mu bar or mu tilde of xt would be that. Only problem being that I don't know what epsilon is, I think. Minus this random that we have. Jesus, this shit is so confusing. So it's saying we could get x0 if we subtract epsilon, and if we have epsilon, and we have xt, because we can only get xt from epsilon, then we could get x0. Okay, and in this case we don't have epsilon, we only have xt, or the reverse step, I guess I should say. We only have xt. Yeah, we only have xt. We're trying to get xt minus 1. C minus 1. We have xt, we have 0, we have epsilon. We also have, so we're given epsilon from that one, in that one forward step we're given epsilon, right? Or epsilon. Then you reparameterize it. Okay, I think I understand. So if we could find the epsilons, if we could approximate the total epsilon and multiply it by this factor, which has to do with the time step, then we know the amount of noise that has been added to the image to end up with xt. And if we subtract that from xt, multiply it by this other constant, which I assume is from the recursive probability distributions through time, then we'll end up with the mean of xt, and the mean of xt is supposed to be xt minus 1. Right. So the loss function could be expressed as, whoa, why do we have this whole term over here? Should it not just be that? Should it just not be this term over here? How do we end up with 1 over 2 and the what does 2 mean again? I forget what that means. Yeah, that's the L2 norm squared. L2 norm squared error, is that what it's saying? 2 times, well, we're not even getting variance, right? It's pre-calculated for us. But yeah, I mean, we only really need to calculate the different epsilons, right? Epsilon dql. I assume it has something to do with the just the way that ql is. I don't know why they multiplied this by 2. And this seems about right. Epsilon minus that epsilon. That's the only thing we really need to find, right? We have some weighting term. I don't know where the weighting term came from. We're just, you know. So yeah, then there's the post by Lillian. I'll have to read this sometime in the future, to be honest. This is, I mean, I guess understanding this is kind of necessary if I really want to make some big, what am I looking for? Big contributions in the future. Is there a video going through Lillian's blog post? Lillian, what's her last name? Wang? Yeah, Wang. Diffusion. I might have to watch this later though. Blog post. No. Another question I had though was, who wrote the DDPM paper? DDPM paper. Written by Jonathan Ho. You know what? I might as well go on Twitter. Jonathan Ho. I don't see any Jonathan Ho. Okay, H.A. Chain. who else are they? Is he followed by? Martin. Okay. Peter Abil. Haven't heard of that name before. Professor at Berkeley. Pretty cool. Who else are you followed by? Alright. Anyways, what was I looking for? Really quick though. Alright. So okay, I think now I'm kind of at a point where I could apply this. We have the loss function, which is the most important part, and then there's these algorithms. So repeat. So this is the training algorithm. I think I wrote this down in VS Code actually. Maybe I didn't. And actually, I'm gonna delete all this because I don't want to use this dude's stuff. Actually, maybe I'll keep the data loader stuff. Keep that. You know what? Maybe I was a little too quick. Keep the imports. I'll keep this. I'll remove. I'll remove this. Device. Oh, torch not fine. Okay. Put these constants over here. And actually, can I just run this, or is it going to chime down again? Okay, it didn't download again. All right, that's all I wanted. Okay. So how do I transform it again? Resize, right horizontal flip, 2 tensor. Okay, lambda, 2 negative 1 1. Okay. Show tensor image. Alright, I'll have to write that. Here, I might as well this over here. I don't need an additional block. Okay, I kind of want to delete this because I want to do it myself. Alright. I kind of want it there too. Can't lie. shit. Let's see. Alright. Oh yeah, so the training algorithm, I guess I might as well write the algorithm first. I just comment it. I'll do this later. Why do I not have my oh, it's still there. Oh, okay, no, it is still there. Okay. Yeah, training algorithm x0 sampled from qx0. Okay, so I already haven't written. So might as well read. X0 sampled from q of x0, t sampled from uniform distribution from 1 to capital T to terminal, epsilon from normal 0I, take gradient descent step on the gradient of epsilon minus the true epsilon minus our predicted epsilon of this, which is supposed to be xt, I believe. Yeah, this is xt. I believe. Yeah. And then for sampling, xt is samples from a normal distribution. For t in t, for t equals t down to 1, z is sampled from a normal distribution if t is greater than 1, else z equals 0. I guess just to give it some variance. Then xt minus 1 equals, yeah, equals this. Okay, so that's what I was saying earlier. Yeah, this would be xt minus 1. xt minus 1 equals 1 over the root of alpha t, with xt minus 1 minus alpha t over the root of 1 minus alpha bar t, epsilon theta plus that z term. Sigma t. I assume that's a scheduled randomizing constant. One thing we haven't mentioned so far is what the model's architecture looks like. Okay, so before that, I might as well start with the being able to with the forwards process is what I mean. Okay, so let's say, yeah, forward diffusion sample. I guess I gotta put that def for diffusion sample. This will take an image and will also take t. Image, I don't know, we could say it's a should I have it in NumPy or PyTorch? To be honest, I don't think it matters. I don't have that saved anywhere, do I? Nope. Okay. So what that should be is it should be following one of these algorithms. So I'm gonna have this on my other screen. You guys can't see. Where is it? You guys, there's not even one person watching. Jesus fucking Christ, where the hell? Or actually, you know what? It's probably have it over here, right? Okay. Wait, actually, maybe it says it. No, it doesn't. All right. The reparameterization trick. That's what I'm looking for. Okay, q of xt given x0. So that would be equal to, so image equals image well, it would be the is there a math dot square root of, yeah, I still have this stuff over here. Linear space, is that what it is? Gotta ask ChatGPT. Torch dot lens space. Evenly spaced points, right? So start and time steps, that's capital T. Linear beta schedule, okay, that's my betas. Pre-calculate different terms for closed forms. So alphas equals 1 dot minus betas. Alpha's cumulative product equals torch dot cumulative product alphas across axis 0. Yeah. Let me just make sure. Torch dot comprod. What a fucking, that name, bro. I'm so immature. Okay, anyways, well, I know what it does. Torch comprod prev equals f dot pad. Right, I don't know what that is, so I'll delete it for now. Posterior variance, I'll keep this deleted for now. Equals comprod square root recipes alphas. Oh, okay, so torch square of 1 over alpha. Oh, you know what? I do know what these are. Never mind, I don't. But I know what these are. Can my lights come back on, please? Lights. Ugh. I swear. Alright. Let me take my hood off. Ooh. I was looking for an. Did I zoom in? No, I didn't. Okay. Yeah, square root of alphas. Okay. Torch dot square root alphas comprod. 1 minus alphas comprod. Okay, well I know I need these for now at least. So I'll use torch dot square root actually. Torch dot square root. Image equals, I have the equation. Torch dot, well actually I don't need to do torch dot square root. It would be the recipe, the, what is it? Square root recipes alpha? No, square root recipes alpha is comprod. Square root alpha is comprod. Or reciprocal alphas, that's what it is. Square root alphas comprod. Square root alphas comprod times square root alphas, cumulative product, yeah, alpha bar, times image, alphas comprod t times image. And that would be plus, I should have 1 minus, right? Square root 1 minus alphas, alpha bar. 1 minus alphas, what is it? 1 minus alphas comprod? Where is it? 1, square root 1 minus alphas comprod t And then that should be times some torch.rand n, I think. Torch.rand n, random normal distribution. Torch.rand n. Let me, it shouldn't matter, but, you know, just for clarity's sake. Okay, so that should be the image, right? Where's the, yeah, here's the sample. Okay. All right, and we already have beta t, right? Yeah. All right. Okay, so then this should work, right? Please. Oh, motherfucker. Oh, forward diffusion sample is not defined. Oh, did I not? Yeah. Oh, and I'm not returning anything either. Okay, that's a small thing that could be fixed. Let me just say image noise equals now return image noise. Oh, wait a minute. No. Turn image noise. Yeah, I need to, I can't do this all in one line. So I'll say, noise equals torch.rand n. And then times noise. Image noise and noise. I want a scalar. Okay, so I can make this of size 1. But shouldn't I need to like pop it or something? Yeah, I need to do the dot item. Where the fuck did I write it? Oh, here it is. 1, comma. Well, we'll see. Maybe I don't need to do dot item. Oh, it worked. Whoa. Okay. That is not what I meant to do. Well, let's see. Maybe if I do, maybe, I don't know. Maybe it's variant. Yeah, no, that's certainly not what I mean to do. Let's see if I do dot item. No. All right. Well, I'm just curious what it was before. All right. Well, I deleted it, so I can't check what it was before. Well, why is this not working? Image noise equals. Okay. Want to debug cell. Noise, okay, just you know, it's a number, and then image noise. Well, noise. I need to make sure it's still the same. Yeah. And image noised. It should be a 3 by 64 by 64. Oh, wait a minute. No. It's because I'm doing noise. Like all of them are being noised the same. There should be noised individually. So I need to make a noise of size 3 by 64 by 64. So that should be 3 by 64 by 64. And it should not be the item. Okay, I think that'll work. There we go. Okay, but there's something kind of off about this variance though, or about the scheduling. That seems kind of wrong. I mean, it's clearly getting noise, but like, seems way too quick. Oh, well, I am doing it linearly over here, which is not what they use in the paper, if I can find it. Yeah, linear beta schedule. I don't want a linear beta schedule. What was they did? They did a root schedule. Say root beta schedule. So time steps. I will copy this. Time steps. And then let me just make sure if I could open. I think it's supposed to be root of BT DDM paper. Oh, it's over. It's right here. What did they take? They took root of 1 minus. No, what does beta equal? Pretty sure beta was it's a root schedule. Where is BT defined, bro? Oh, BT. Oh, that's BT bar. I know they define BT somewhere. If I look up schedule, which is BT for instead of constant linear and quadratic schedules, all constrained so that LT is around 0. We set T, okay. Oh, actually, I think it's on the next paper, the improved one. Improved, or DDPMs beat GANs, I think. DDPMs beat GANs. Yeah, there it is. Yeah, I guess I could do linear scheduling. Schedule. Alright, I want to go back to the first one. What is a cosine schedule though? Would that be from 0 to 1? What? Cosine scheduler. Alright, you know what? I'll just keep it simple. I'll keep it on linear. here. So, alright, so we have this, when you're, Jesus, why is this such a huge fucking margin? Oh my god. If I did 30 by 30. Well, they're bigger, but like... Okay, what if I did num images too? Bro, why is there such a big fucking space? Oh my goodness. 10. Alright. Alright. PLT subplot. What if I remove the subplot? Oh my god. Alright, no, we'll keep that subplot there. I guess there's nothing I can do about the margin. Alright, okay, so you know what, let's save this to Git. ls, actually, what's it called? Pipenv activate deep learning. Huh? Okay, you know what? Are you... Maybe it's PyEnv? Oh, there it is. Deep learning. Okay, now, what was I looking to do? Oh yeah, git, no, well, cd, I think it's, oh, fucking hell, ls, cd, what is it called again? Image diffusion. Oh my god, I need to definitely add a git ignore. Okay, good. Status. Basic. Initial setup. Okay, so now we could, well actually first I need to make the UNet. They added the, I mean, I guess I could make it myself, but, or make it completely independent, but it's not quite a ResNet. Yeah, I'll make the UNet. So, architecture. One thing we haven't mentioned so far is that the model's architecture looks like, okay, so the sound, UNets, feel free, okay. Yeah, so its output would be the noise. Let's see something real quick. If there is a viewer right now, which I can't tell, feel free to type in chat. Unit is a okay. The unit consists of wide resonant blocks, group normalization. No, resonant blocks are. I forget what group norm is. Is it batch norm? Is group norm just a batch norm? All right. Just need to check something real quick. All right. Oh, this is Yannick Kilcher? Oh shit. Hold up. I'm certainly following him. V Japa. Alright, anyways, I'm gonna have to watch a video on this. I just wanna know what group norm is. Group normalization. Oh, don't. I'm not really gonna watch a 30-minute video. I mean, the focus of this is not group norm. Oh, fuck me. Okay, alright, yes.
This U.S. Open office plan.
Miller just lobbed a message way over Jones's head using some technical jargon.
Hi there. Today we'll look at group normalization by Yuxin Wu and Kaiming He of Facebook AI Research. So this paper is basically an engineering paper about a new normalization technique called group normalization. So what's the issue here? The issue is that pretty much throughout neural network learning, we're using this technique called batch normalization. Now, batch normalization is a pretty reasonable thing and it works very, very well. So what's the idea behind batch normalization? The idea is if you have data points for machine learning methods and your data is in a 2D coordinate system somewhere down here, right, and you're trying to separate that from the dots, which are here, it is often very beneficial to shift that distribution before you do anything. You want to shift it to the middle of the, basically want to center it first of all, such that the origin point is in the middle of the data. And then sometimes you also want to do what's called normalize it. And by normalizing, we mean you want to kind of rescale the axis such that things are more or less sort of like Gaussians. So if you look at this distribution, first is the centering, and then second is what is called a normalization. And usually we know that any sort of machine learning methods work better if you do that, and that's mostly in classic machine learning methods with conditioning numbers of the data being better and so on. But if you just want to learn, let's say, a linear classifier, you can see here, you can even save one parameter because you can make it just go through the origin. And that's true in general. So if we draw this in 1D, you'd have a distribution that maybe is very peaky right here. You first center it to the middle of the coordinate system. And sorry, that's not really centered. And then you would divide it by its standard deviation such that after it is a unit standard deviation Gaussian, so a normal distribution. The closer your data seems to be to a multivariate normal distribution, the better these machine learning methods work, especially if you look at how signal in deep network is propagating through the layers. So the idea is, if it's good for the general machine learning method that the input has a multivariate normal distribution or is normalized, then it's probably good that the input to each layer is normalized. So when you look at how signal features are in between layers, so this is, for example, the conv53. This is a layer somewhere in the middle of a convolutional neural network. And if you look at the spread of how feature signals are throughout training, you'll see that the more training progresses, the larger the kind of spread of features is. So you might get really large numbers or really large negative numbers or maybe really small numbers in your neural networks. And it would be better if you had a layer and the input, you've normalized it, right? And the output then is again a distribution, but it's maybe shifted. That you would first transform that back into a normal distribution before you put it through the next layer. So what batch norm does is at each layer, before each layer, it will do a normalization procedure on the data before giving it to the next layer.
Don't know what batch norm does?
And you can do basically backprop through that. It's also common to learn bias and variance parameter to add after that. But the important thing is that after each layer, the data is normalized such that it is kind of in the most comfortable regime. What's the problem? The problem with this is that you actually need the distribution, right? If you want to center this data up here, you need to know what the data is. So you need to know the entire data. If I want to figure out what is the mean of this distribution, I need all of the data points to decide here's the mean. I need to shift that up to here. If I just have a mini batch, like we usually do in machine learning, so if I just have this or this and this and this point, I just have 4 points, I can't determine the mean. But what I can do is I can sort of guess the mean from the 4 points, right? So my guesstimation of the mean would be somewhere here. And that would be usually close enough. And you can also see that the larger your batch is, if you sample at random, the more accurate your mean estimation is going to be. So people have been training neural networks with large batch sizes for basically batch sizes have gotten larger and larger in the last year, so that has not been a problem. But what people are doing now is they are doing distributed machine learning, where you do have your data set and you draw a batch, and the batch might be large. So this might be, I don't know, 1 million. Million images. This might still be 4,000 images in your batch, but what they'll do, especially with things like TPUs, is they'll distribute that across many machines into batches of sometimes as small as 8 samples per unit. And if this is not images, but maybe something longer, like a sequence of text, or if this is a sequence of speech or something like this, you can sometimes even go down to 2 or 1 samples per unit of computation. And of course, you can't do batch normalization. You can't calculate a mean of 1 sample. It's just going to be that 1 sample itself. So either you have 2 options if you're in small batch sizes, let's say 2. Either you take the hit and have your very bad estimate of the mean from just 2 samples or 8 samples, or after each layer you basically do a synchronization step such that everyone communicates to everyone else their statistics, and you can basically aggregate the statistics across the batch. Both are not cool. Usually these frameworks, they don't do this synchronization because it's just too slow, so they'll go with the bad statistics. And you can see this right here in this graph. They have the ImageNet classification error versus batch sizes. So this is a ResNet 50 model trained on the ImageNet dataset using 8 workers, so 8 GPUs. And if they do 32 images per and then in addition to that, now just look at the blue line here. If they do 32 images per worker, so it's 8 workers, it's 8 times 32, that's the batch size. That is a large number, 256 maybe, yeah. All right, so if they do that, then you can see the error is on a state-of-the-art for a ResNet 50. If they go to 16, it's still pretty good, but then as they go lower and lower and lower, so if they go to smaller and smaller batches and spread them out over the workers, then the error starts going up. And this is because the batch norm statistics get worse and worse. So the goal of this paper is to find this group norm thing here. The group norm, this paper claims, is another normalization technique that pretty much does the same thing, this centering and the normalization, the scaling, but it does it without relying on the batch statistics. It basically does it within a data point. And that means that the performance, even though it's a bit smaller at the beginning for this particular example, will stay constant with even in small batch size regimes. So this is potentially applicable, as I said, to things where you have to go to like 2 or 1 sample per worker because it's just the data points, the single data points are just too large. So if you maybe want to train something like BERT on a GPU. So what is group normalization? Group normalization as I said, works within a sample. Now, there have been other methods that work within a sample instead of across the batch. And they tend to not work as well as batch norm. Now, this paper here claims that group norm works on par with batch norm for large batch sizes and better than on small batch sizes. So here they have a schematic of what's happening. In batch norm, as you can see here, you have this cube. Now this cube here, n, means the batch size. So these are the data points in your mini batch. This is the thing that is going to get small if you don't have enough.
All right.
Memory.
I'm back.
Then C would be your channels. So we are talking about convolutional neural networks here, but this is generalizable to other neural networks. The channels are going to be the independent feature maps that you're going to have. So in a convolutional neural network, usually each layer has these things called kernels, and there might be 3 by 3 matrices like this. And if you have an image, the kernel will be slided. This thing right here will be maybe here, will be slided across the image, or slid. Is it slid? Okay. Will be slid across the image, and then the numbers in here will be convolved with the pixels, and that will give you the next layer's representation. So whatever the convolution operation is, and you'll slide that over, and that sliding over will give you the values in the next layer. Now you not only have one kernel, but you actually have many kernels. Sorry about this. Let's draw that. So you have more and more kernels. Zip. Zip. You have a whole stack of kernels, and how many kernels you have, those are the different kernels are also called your different channels. Now, the kernels refer to the weights and the channels refer to the image, but the ith kernel is going to be convolving the ith channel of the image. So at the beginning, the input image has 3 channels because red, green, and blue. But then the intermediate images can have more channels as you have, as basically as many as you have kernels in the layer right before. Okay, and the H and the W means the height and width of the image. So it combined. So the image is kind of unrolled across the height or the width in this direction. So what does batch norm do? Batch norm takes, as you can see here, one channel, and it takes one channel.
So this is a representation of pixels then?
Maybe this image, this is one channel. Let's just say this is the red channel because I've drawn it in red. It takes that and it calculates the mean 1 over and the standard deviation of that. It calculates those two statistics and it uses that to do this centering and scaling operation. So all of these methods are going to calculate the mean and the variance and then do the same scaling transformation. The question is just how do you calculate the mean? Batch norm does this across the data points. So it looks at a single feature at a single channel and it asks, what's the mean across all the data points? What are the data statistics of this channel? And what's the mean and standard deviation? What's the mean and standard deviation? Now, actually, batch norm, I didn't even know that in convolutional layer this works like this. You can also imagine batch norm of really just taking one single feature, and that means of really just taking one of these things right here.
Yeah.
This goes back. And
Jesus.
Normalizing across that. The important part is that it is, in fact, normalizing across the data points. So
but hold up.
now, across all signals and then and the standard deviation of that. It calculates those two statistics and it uses that to do this.
But the thing is that these aren't normal distributions though, or they're not scale normal distributions. And if I'm taking individual neurons or nodes, I could expect that to be a normal distribution. Or that seems more intuitive to me, but this doesn't.
And scaling. The beginning, the input image has 3 channels because red, green, and blue. But then the intermediate images can have more channels as you have, as basically as many as you have kernels in the layer right before.
So I'm taking pixel.
Okay, and the H and the W means the height and width of the image. So it combined. So the image is kind of unrolled across the height or the width in this direction. So what does batch norm do? Batch norm takes, as you can see here, one channel, and it takes one channel. So maybe this image, this is one channel. Let's just say this is the red channel because I've drawn it in red. It takes that and it calculates the mean 1 over and
this is
the standard deviation of that. It calculates those two statistics and it uses that to do this centering and scaling operation. So all of these methods are going to calculate the mean and the variance and then do the same scaling transformation. The question is just how do you calculate the mean? Batch norm does this across the data points.
Does it? I thought it was across each individual perceptron. I need a pencil for this. So if I have take the average of that point, I think it was the standard deviation of everything.
So
actually, I have a good explanation of this that I made, or when I understood it at least. The average mean of a layer output is more volatile. The average mean of a layer output becomes more volatile. This compounds the deeper we go. Is it across all of these? So it'd be like that. Yeah, so we do this across individual samples, or across individual features, I mean. I don't think it was across, normalize, features, scale, and shifts, yeah. Okay, that was my understanding, but he's saying that we do it across this entire square, which is not what I thought happened.
it looks at how on its national norm for large batch sizes and better than on small batch sizes. So here they have a schematic of what's happening. In batch norm, as you can see here, you have this cube. Now this cube here, n, means the batch size. So these are the data points in your mini batch. This is the thing that is going to get small if you don't have enough memory.
So
then C
number of
would
samples,
be your channels,
and pixels. So this would be pixel HW.
We are talking about
channel,
convolutional neural
C.
networks here, but this is generalizable to other neural networks. The channels are going to be the independent feature maps that you're going to have. So in a convolutional neural network, usually each layer has these things called kernels. So we are talking about convolutional neural networks here, but this is generalizable to other neural networks. The channels are going to be the independent feature maps that you're going to have. So in a convolutional neural network, usually each layer has these things called kernels, and there might be 3 by 3 matrices like this. And if you have an image, the kernel will be slided. This thing right here will be maybe here, will be slided across the image, or slid. Is it slid? Okay, will be slid across the image, and then the numbers in here will be convolved with the pixels, and that will give you the next layer's representation. So whatever the convolution operation is, and you'll slide that over, and that sliding over will give you the values in the next layer. Now you not only have one kernel, but you actually have many kernels Sorry about this. Let's draw that. So you have more and more kernels.
Let's help Palestine out right now. They need food, they need water, they need medical supplies. No other country.
Zip.
They just zoomed in again, didn't it?
You have a whole stack
Yep.
of kernels, and how many kernels you have, those are the different kernels are also called your different channels. Now, the kernels refer to the weights, and the channels refer to the image, but the ith kernel is going to be convolving the ith channel of the image. So at the beginning, the input image has 3 channels because red, green, and blue. But then the intermediate images can have more channels as you have, as basically as many as you have
so
kernels in the
there.
layer right before. Okay, and the H and the W means the height and width of the image. So it combined. So the image is kind of unrolled across the height or the width. Basically, as intermediate images can have more channels as you have, as basically as many as you have kernels in the layer right before. Okay, and the H and the W means the height and width of the image. So it combined. So the image is kind of unrolled across the height or the width in this direction. So what does batch norm do? Batch norm takes, as you can see here, one channel, and it takes one channel. So maybe this image, this is one channel. Let's just say this is the red channel because I've drawn it in red. It takes that and it calculates the mean 1 over and the standard deviation of that. It calculates those two statistics and it uses that to do this centering and scaling
That is
operation.
not what
So
batch
all of
norm
these
does.
methods are going to calculate the mean and the variance and then do the same scaling transformation. The question is just
didn't think so.
how do you calculate the mean? Batch norm does this across the data points. So it looks at a single feature at a single channel and it asks, what's the mean across all the data points? What are the data statistics of this channel? And what's the mean and standard deviation? Now, actually, batch norm, I didn't even know that in convolutional layer this works like this. You can also imagine batch norm of really just taking one single feature, and that means of really just taking one of these things right here.
That's what I thought it was.
So this goes to the back, and normalizing across that. The important part is that it is in fact normalizing across the data points. So it looks at your batch, looks at the mean and the variance in that batch, and it normalizes by that. I think convolutional layers make sense because you have this invariance in height and width, and therefore, yeah, so that makes sense. But in a fully connected layer, you'd simply you look at one feature at a time. Layer norm is different. Layer norm has basically been proposed as an alternative to batch norm with the same reasoning that this paper has. So layer norm, as you can see here, it does each data point individually. So here we only have one data point that is normalized by itself. So you do this for each data point independently, and therefore it's not dependent on the batch size anymore. But what you'll do is you'll look across all of the channels right here. So all of the channels and all of the width and height. So this entire thing here, this entire thing is basically one channel, right? And then the next channel is here of the image, and the next, no, that's the next image. Well, that is a bad drawing because the image is unrolled. In any case, what you'll do is you'll look at, so if you have a filter bank like this, you have an image, and the image is composed of multiple channels, right? This is the red, and then you'll have the green, right? This is in the green, and then you'll have the blue channel. And what you'll do is simply you'll calculate the mean across all of the pixels and across all of the channels. You just take this whole NumPy array and you just say dot mean, and that gives you one number. And it's just whatever that number is, you subtract it, and then you say standard deviation and you divide by that. That's layer norm. So an entire layers representation of one image is just normalized to the mean. Now this seems a bit drastic, and that's why instance norm did the exact opposite. They said, wait a minute, instead of normalizing across all of the features, right, we'll go back and do what batch norm does. Batch norm looks at each feature individually. So basically it looks at all of these different axes in the data distribution. It looks at them differently. So if one axis is scaled very widely, we want to normalize that differently than the other axis that is just scaled very shortly. And that's why we'll look at each feature individually like batch norm, but also we only look at one data point at a time. Now, as you can imagine, this doesn't work anymore in a fully connected network. This basically works in a convolutional network where you have a feature map channel. So you look at one individual channel and one data point. So that means here you would normalize the red channel individually, you would normalize the green channel individually, and you'd normalize the blue channel individually. So the image you're going to end up with is simply the red channel subtracted by its own mean and then divided by its own standard deviation. And just within that data point, right? So maybe I should here say across the number of features or something. So I hope that's clear. So the layer norm drops the dependence on the batch size, but instead says we should normalize across all of the features. And the instance norm says, wait a minute, batch norm had a good idea normalizing only across the features individually because the individual features might have different scales and we should account for that. But also we don't want to be dependent on the batch size. And now this is where group norm comes in. Group norm is basically a mix between layer norm and instance norm. What group norm says, layer norm and instance norm have good ideas. They only go across one sample. They take that. They say, in essence, instance norm has a good idea in that the features should be normalized individually, but it goes sort of too far from, it goes too far. You might get not good enough statistics because you're now normalizing each of these things individually. Whereas with layer norm, you're too restricted. You're basically saying that the features, it's fine if the features relative to each other are like this, right? One is maybe very high variance and one is very low variance. Feature norm would keep that, and group norm would say maybe it's not so good. We should normalize the individual features, maybe individually. But their argumentation here is that maybe there are some features that by their nature already have the same sort of scaling and variance. They give an example. If you, for example, have a filter, again, we deal with convolutional. Layers here, and that filter is a let's say an edge filter, right? So a horizontal edge filter, so it's very low value here, and let me mark the high value with blue. So this is a horizontal edge filter. If you slide this over a window, and these are high numbers and these are low numbers, it will respond to edges because edges have high, low, high, right? Or vice versa. So it will give you very positive and very negative number every time you slide across an edge. Now you can imagine that in natural images, that filter, whatever image you put in, would, and however you normalize, would give you pretty much the same response as a vertical edge filter.
This Ramadan, in Gaza, tables are bare.
Window, and these are high numbers and these are low numbers, it will respond to edges because edges have high, low, high, right? Or vice versa. So it will give you very positive and very negative number every time you slide across an edge. Now you can imagine that in natural images, that filter, whatever image you put in, would, and however you normalize, would give you pretty much the same response as a vertical edge filter. So the horizontal and the vertical edge filter, you'll see whatever their response is, they're probably about equal in size. So we could expect
Wait, what?
the response as a, imagine that in natural images, that filter, whatever image you put in, would, and however you normalize, would give you pretty much the same response as a vertical edge filter.
No.
So the
fuck?
horizontal and the vertical edge filter, you'll see whatever their response is, they're probably about equal in size. So we could expect that in a neural network there will be groups of filters that together exhibit the same scale, and therefore we can normalize across them, like in layer norm. So the more things we normalize across, the better statistics we can gather. That's why instance norm doesn't work, because it only normalizes across a very small thing, getting very little statistics. But we should normalize, if we could gather good statistics, we should normalize different features differently. And group norm says, well, since some of the features are almost guaranteed to behave the same, we could normalize across those. Now, of course, you don't know at the beginning which ones those are. So, but you hope that by doing group norm, by basically a priori, so at the beginning of training, you decide what the groups are, and naturally it's just whichever ones are next to each other, those are the groups. You'll hope that through the training procedure, basically those groups will learn the features that are equal of size. Well, you basically enforce that. So you kind of constrain the architecture to do that. So that's the idea behind group norm. You basically build these groups of channels, and then you normalize across those, across the groups of, within the groups of channels, across the entire height and width, only in a single data point. And therefore, you gain the advantage of layer norm, of normalizing within a single data point. You retain the advantage of batch norm, of normalizing across single features. That's what instance norm attempted. But yeah, so you get the best of both worlds, sort of. That's group norm. And now we go and look what it does. So they say, okay, basically all the normalization techniques do this. They subtract the mean and divide by a standard deviation. That's what we saw. And the difference is just across what you collect your statistics. So the group norm is the following code in TensorFlow. As you can see, you simply reshape your data and basically you expand this part right here where where you put the extra. So this is C. This entire thing used to be C, and you divide it into group and index within group. And then you just normalize across that and reshape to the original dimension again. And the cool thing is, in batch norm, you have to keep track of these running means, because at test time you sort of don't want the batch statistic to influence anything. You don't have that here. You could just backpropagate through this operation, and you don't need to keep these running averages going, and you always care, am I in test or am I in train mode right now? You just do this operation is per data point. So it's just part of your model, right?
Yeah, that's to reduce covariate shift.
And they
right?
do an experiment where they have 32 images per GPU, so it's reasonably sized, and they can basically show that the group norm and the batch norm, they compare in their performance. Now, I usually don't believe the experiments that you see in single papers, but I think this has been replicated a couple of times now. You see, this is the train error where group norm even behaves a bit better, and then in the validation error it behaves a bit worse, but one could say it is kind of more closely together than the other methods are to the group norm or to each other, these instance norm and layer norm. So at least it's better than instance norm and layer norm. And then once you go into the smaller batch size regime, of course, that's where the group norm starts to shine. So if you go from the 32 images per GPU, which is this low black curve here, all the way to 2 images per GPU, and I believe they could even do 1 image per GPU with group norm, but of course you can't do that with batch norm.
How long is this paper? Alright, I can read it. So this normalizes, well, first normalizes features within each group rather than normalizing features across batches. But how does that reduce covariate shift though? Does group norm reduce covariate sperm count? Covariate shift. Oh, that's my question. Well, I guess actually it could reduce covariate shift if I'm if I am if I'm normalizing across the entire channel, then I could expect that a gradient update later, the proportions between each features will, is that a spider? Will be somewhat the same, right? Will be near the same, as long as the gradient step is small enough. I think, but their mean could vary wildly though. So that will be centered across something completely different. I wonder if this still uses gamma and beta. The fuck? How do you... Oh. Well, if the target data distribution changes, then the entire model wouldn't work, right? Yeah, so this as we saw earlier was not totally right. How much more? I want to get back to diffusion, oh my god. Alright, well, I feel like I generally get the idea. Okay, these are testing. Okay, I just need to read this in the next page. Until implementation. Okay, up until experiments. Alright, that's not too much. You first describe. Oh. xi hat equals 1 over, wait, we first describe a general formulation of feature normalization and then present group norm in this formulation. A family of feature normalization methods including Bn, Ln, In, and Gn perform the following computation. Xi hat equals 1 over standard deviation times xi minus the mean. Here x is the feature computed by a layer and I is the index. In the case of 2D images, I equals IN, IC, IH, IW is a 4D vector for indexing the features in batch, channel, height, width order, where N is the batch axis, C is the channel axis, and HW are the spatial height and width axes. Mu and sigma are the mean and standard deviation computed by mu is 1 over m with what is m supposed to be? I mean, I know m is supposed to be the cardinality of x, right? For k, the fuck is k? Thanks for telling me, bitch. Okay, Jesus. Actually, shouldn't it be 1 over x? Or no, it's x. I'm assuming m is the amount of, like, the amount of loops, I guess you could say. Standard deviation formula. So I'm taking the distance squared plus epsilon. Don't know why. I guess it can't be 0. SI is a set of pixels in which the mean and SED are computed. M is the size of the set. Okay. Any types of feature normalization methods mainly differ in how set SI is defined. Match from the set SI is defined as SI is the set of K given KC equals IC. K channel is I channel, where IC and KC denote the subindex of I and K along the C axis, channel axis. It's actually usually KCHW, that's my understanding. Showing the same channel or normalize together. Pixel, oh. Okay. Sharing the same channel are normalized together. The same channel being commutes along the NHW axes. The norm of the set is SI equals the set K, where KN equals IN. Meaning ln computes mu and sigma along the C channel height width axes. So what would that look like? I think it's like that. Since term SI equals K, where KN equals IN and KC equals IC. What is that KC equals IC? Where the channel is equal and alright. Meaning that instance normal computes mu and sigma along the height width axes for each sample and each channel. The relation along the batch norm ln or figure 2. All methods of learn a per channel linear transformation to compensate for the possible loss representational ability. Yeah, this gamma plus beta, where gamma and beta are trainable scale and shift indexed by IC. In all cases, which you omit. Group norm, formerly a group norm layer, computes mu and sigma in a set SI defined as SI is K. Is a set of K where K n is in. So it's within the same sample, or same batch. No, same sample. Kc and C over G, and IC equals IC and C over G. So it needs to be in the same channel group. Kc divided by C over G. Here G is the number of groups. 2 over 6, 3 over 6. Which is a predefined hyperparameter. G equals 32 by default. C over G is the number of channels per group. Oh, okay, there's a for operation. It's a for operation and means that the indexes I, K are in the same group of channels, assuming each group has group of channels are stored in a sequential order along the c-axis. Gn computes mu and sigma along the height width axes and along the group CG channels. The computation of group norm is illustrated in figure 2 rightmost, which is the 3 channels. Given S, I, in equation 7, a group norm layer is defined by equation 1, 2, and 6. Specifically, the pixels in the same group are normalized together by the same mu and sigma. Gn also learns the per channel gamma and beta. What would that be like? Yeah, I mean, I guess I understand. If I could open convolutional neural representation. So, yeah, we end up with this feature map. We normalize that feature map along like these three. Then we'll apply some gamma and beta transformation to it to restore some representational ability. I guess this would be after ReLU. Oh, well, actually, I don't know. It could be before or after ReLU. I assume it's before. Group norm before or after ReLU. Group norm before or after ReLU. I assume it's placed before. Alright. The fuck? Where was I? Oh. So group norm X gamma beta G epsilon. X input features with a shape NCHW. Gamma beta scale and offset with shape 1C11. Oh, 1C11. Why is it not just C? Or 1C1. X N G group C divided by G HW. Huh? Okay, so I guess we're providing another channel dimension. And yeah, in that group you can index the channels. Alright, that makes sense. Well, I guess we'll need it for later. tf.nn.moments. I guess this calculates mean variation. Alright, bro. Yeah. X tf.nn.moments. Okay, well this calculates the, I guess you pass x, the dimensions. So 2, 3, 4, 0, 1, 2 cross channel 3, 4. X equals x minus mean divided by tf dot square root of variation plus epsilon divided by the standard deviation. X equals tf dot reshape x nc hw. Yeah. I mean, I wonder how it automatically knows that, you know, this should be absorbing, like the G should be absorbing those both. Oh, well, I guess given the other parameters. Turn x times gamma plus beta. Okay, so gamma plus beta is applied across the entire thing, right? That doesn't look like it's per channel. Unless gamma and beta is okay, yeah, it's yeah, all right. All right, well, I think I overall understand. We could get back to oh Jesus Christ, to this. So where was I? Instead of wide resonant blocks, group normalization, as well as self-attention blocks. I'm not going to look into self-attention. I mean, I understand the basics of it. I have an idea of it. But I forgot most of the math, to be honest. Query, key. What is it? You have the query and the key, the query and the key, and then you get the value. And some other shit, I don't know. I can be right back. I'm gonna get some food. Alright, I'm back. I have saltines. Jesus. Alright. So we're gonna make a unit without self-attention. Bye bye. Alright, we are back. I'm gonna put my hood on because I opened the window. It makes me look gangster. Alright. So where was I? Oh yeah, I need to make the unit now. Excuse me. Oh, fucking hell. This shit, we really have to zoom in now. Okay. We're good. So, forgot how I go about making a model. I'll go back to my to my previous thing. So yeah, I have ConvNet over here. No, actually, well, first of all, I think I'll start by making a new file for it. Simple unet.py. Alright, now, what was I looking for? Oh yeah, I want to look at my resnet.py. So, I could kind of just copy this, right? But, you know, I forgot so much, I like to remake it. So, yeah, actually, how is a... Forgot what the components I need for ResNet are. What do I have two different... Okay. Alright. So you dance sample it, it's like some wait in space and bring it back up to, that's what it is. So unet implementation, or not implementation, unet paper. Do they have a, that's it? You know, I mean, I could read it. Alright, we are going to, I guess, go about it on my own. So class, or I might as well do my imports. Import, I'll just import all of it. Okay, now class simple unet. Here it's from nn.module. Now def init. Bro, do you really have to do that? Actually, you know what? It shouldn't matter. Simple unit. Actually, I might pass in some shit. Yeah, so we're gonna have, I guess we could define it over here. So what I want to do is go from a feature size of 64 by 64 to, I don't know, 32 by 32 to 16 by 16 to 8 by 8, and then to 32 by 32, or not, to 16 by 16 to 32 by 32 to 64 by 64. And I guess, yeah, we're doing a bottleneck, right? So 64 by 64, channel is 3 by 64 by 64, and then 6 by 32 by 32, 12 and then 24. And that's kind of low, to be honest, but here's and then 12, 6, and 3. Let me ask ChatGPT. Why did the amount of views I got on the stream go down? I was at 5 and now it's at 4. Okay. Is this channel X feature map size the implementation of a UNet? Do you think this is enough layers? Enough, yeah, layers for a diffusion model. All right, 3, okay, 6, 12. I guess I could do 3 by 64 by 64. To 3 by 64 by 64. To, I guess I'll just double them. Okay, so what would that require? So self dot conv 1 equals input size of 64, or in, I think that's what it is. Oh, actually I need to do conv, or torch, is it torch.conv? Torch.conv 2D. I swear, is that what I do over here? Or nn, okay. nn.conv 2D. And in channel 64, out channels 64, kernel size of, God damn. So width new equals width minus, I think it's probably 3. Actually, I have a calculator right here. Okay, so on, I want to do 64 minus 3 plus, I don't know, plus 1. Or no, plus, no, 64, Jesus, minus 3 plus 0 divided by 1 plus 64 minus 3 equals plus 1. It's 62, so I guess a padding of 1. 64 minus 3 plus 2 plus 1. So I'll use a padding of 1 for 3 and a stride of 1 and a padding of 1. Okay. And then self.conv 2 equals nm.conv 2d, same thing. Actually, no, not the same thing. I want 64 output size 32, and then I guess a 2x2 convolution with a stride of 2, that should be good. So a stride of 2 and a padding of 0. I think that would work. So 64 minus 2 equals plus 0 divided by 2 plus 1. Yeah, okay, that's correct. Alright. And then I guess I could copy this. Self.conv 3 equals 32 3 1 1. Just to make sure that's correct. 32 minus 3 plus 2 plus 1 equals 32. Alright, so I could then copy this. 32 16. Oh, this is channels. Oh fuck. God damn it. Alright, no, this is not 64. So there should be 3, 3, then 3, 6, 6, 6, then 6, 12. And then self dot self.conv 4. How did the views go down to 2? Bro, it was at what? I was at 5. How did the views go down? Bro, I'm actually so confused. Oh, you know what? I think it's off the graph now. Yeah. Okay. Now, this is, I'll just keep track. 64 by 64. 60, no, it's 32 by 32. Then 32 by 32.
Want to become a certified project manager but aren't sure about the skills you need? The PMP certification.
Then it's 16 by 16. And then now self.conv 5 equals Wait, what? The output is 16 by 16. Okay, and then there should be 12 to 24. And then we do 24 to, no, this is 8 by 8. Okay, where's the actual implementation? That's what I want to know. Oh, network architecture. Okay. Alright, well, I could just do that. I just make sure these, what is this 284 and this 282? 1040, 1038. Alright. Oh, it's because they use the valid, yeah, I see. They use the, what that guy was talking about earlier. The valid mode to discard the pixels that are out of the edges. Anyways, I'm not gonna do that. I'm looking for fucking VS Code, Jesus Christ. Yeah, so, I might as well save it as blocks. Class block and then dot module def init super block dot init. We'll pass in the input channels, output channels. Actually, no, just input channels and input size. Okay. So I want to have a self.conv1 equals nn. Oh, whoops. No, that's right. Self.conv1 equals nn dot. What the fuck is wrong here? Self is undefined. I'm within def init. Yeah. What do you mean self is not defined? So, oh, I need to pass self in the init. Self.conv1 equals nn.conv2d, and we're gonna do in channels is input channels, out channels is input channels, then kernel size is 3, padding of 1. That's what I did. Okay, then we'll do self.conv2 equals conv2d, input channels, then it was a stride, kernel size of 3, so stride of 1, padding of 1, and then self.max pool equals nn.max pool 2d, kernel size 2, stride of 2. Okay. And then in the def forward, we'll take a self x. We want to, oh, actually, I'm not sure if I could do that. No, self x. I can do a skip connection, actually. Okay, and then skip x. Alright, I don't know if maybe that's not the most beneficial way or the most optimal way of doing it. So self dot relu f dot relu self dot conv1 x and f dot relu self dot conv2 x and then self dot max pool x. Oh no, x. Why need to do x equals I could pass skip x as 0. That's what I'll do actually. Skip x equals 0. Then plus skip x. I think that should work. Let me just see the architecture. Well, it looks like they only passed it once. Only to the first one. Let's okay, wait. Looking for the skip connections. Oh, concatenation with the correspondingly cropped feature map. Yeah, okay. Wait a minute. It looks like, yeah, hold on. There actually will not be any skip connections because this is what's it called? Down sample block. Down sample block. So there is no skip x. So we'll then return x. Alright, and so we also then need our upsample block. Guess I'll start just by making it. So self dot down down sample 1 equals down sample block input channels 64 input size 64. Oh wait a minute. I guess input size doesn't matter. Oh, Jesus. The fucking back itches. Alright. 64, then self dot down sample 2 equals down sample block. There should be, no, there was 3 at first, and then there should be 6 channels. Right? Yeah, then self dot down sample 3 equals down sample block 12 channels. Self dot down sample 4 equals down sample block with 24 channels. And actually, by the end of it, there will be, so ends up with 6 channels. There should be 48 channels at the end. Ends up with 12. Ends up with 24. Ends up with 48. Okay, so 6, which is 32 by 32, 12, 16 by 16, 8 by 8, and then 4 by 4. I'm not sure, maybe I shouldn't do 4 by 4. Yeah, I won't do that. Keep at 8 by 8. Okay, and then self class up sample block and then dot module. Whoops. Where is it? Alright, def Okay, so how do they upsample again? They transpose convolution. What is a transpose convolution? But how upconv? What the fuck is an upconv? Upsampling convolution? 2 by 2? I guess yeah, you could do 2 by 2, I think. Kind of curious what this paper is about, though. Every step in the expansive task consists of an upsampling of the feature map followed by a 2x2 convolution up convolution that halves the Alright. So, you're learning with me, guys. Well, there's no guys. There's nobody. What is,
You can say goodbye to poor and confusing communication. I'm sure you've heard of.
Scale this image by factor of 2 using bilinear interpolation. So let's do this. So how to apply bilinear interpolation to this image? Simply, what I'm going to do, I will add an empty column between every 2 columns in the original image. So I have 2 columns in this case. So I'm going to add a column between these 2 columns. So in the result, I will insert to the right a new column like this. Okay? So this is the new column. And what I'm going to do is simply, I will get in this cell the average of these 2 cells. So you add 100 plus 50 and divide the result by 2. So 150. That is, so we right click this cell, 7. Now 7. Now this will.
all right, but that didn't double it.
That
That made it 9, not 4. Or 3 by 3 instead of 4 by 4. Well, how did you? You know, I need to learn this anyways, so.
Hello, this presentation will talk about bilinear interpolation. You can find it in the book in section 5.2.1.
What are barycentric coordinates again?
We have 4 points we want to interpolate in a bilinear fashion rather than a linear fashion. So typically we're thinking of we have some curved surface. And sitting on this curved surface.
Oh yeah, that was for something to do with a marching tetrahedron.
X, Y, Z, and W. And they make some rectangular patch, which may not be, if it's actually on the surface, it won't be a perfect rectangle, it'll be some curved object sitting there. But we'd like to approximate the surface by using what's known as bilinear interpolation, which means we'll be using linear interpolation twice. So let me draw another picture of this, which we'll join by straight lines. So these are the straight line segments joining four vertices. And we're going to approximate a point in the middle of this surface by a function.
Wait, I thought this was about image processing.
And you just interpolate. Next.
Bro, I'm like... Just tell me the friggin' algorithm, man. You know what? I'll just abstract it. I hate doing that now. I'm tired of abstracting stuff. So let me undo this. And bro, why are you zooming in again?
In order to scale images. So why is it hard to scale images? Let's start off by discussing the two types of general images, vector graphics and raster images. Vector graphics represent images using Cartesian coordinate points and shapes, for example, polygons and circles. Unlike raster images, vector graphics do not suffer from aliasing. We have no issues scaling vector graphics. Some file formats you might have seen before are SVG or PDF occasionally using vector graphics. Aliasing occurs when real-world objects, which comprise of smooth continuous curves, are rasterized using pixels. We can see here that the letter A is definitely smoother when we apply aliasing, otherwise it has those jagged edges. This is what aliasing occurs, and it occurs in rasterized image. Smoother when we apply aliasing, otherwise it has those jagged edges. This is what aliasing occurs, and it occurs in rasterized images. So raster images, unlike vector graphics, provide a bitmap where each pixel is provided a series of bits to describe its look. The look can be described using various methods, but there's typically grayscale or RGB, so for example sRGB, sCRGB, etc. So if you go to Photoshop or Paint, how does the image resizing actually work? Here's our basic image. We have a height of 3 pixels, and then we have a width of 6 pixels, and it's a 3x6 image, but let's say we want to make it 6x12. How do we accomplish this? So if I go through, I'm going to have to guess what type of color pixel goes there, and also what type of color pixel goes there. So there's 3 simple techniques. The first one is nearest neighbor. The second one is bilinear interpolation, and the third one is bicubic interpolation, which we'll cover in the next video. There's more advanced techniques beyond the scope of this video, such as sync and the algorithm is resampling, neural networks, and more. So nearest neighbor. The algorithm is pretty simple. Iterate over all points in the image. For each pixel in the enlarged image, assign the color to be the color of the nearest equivalent pixel in the original image. You can use Euclidean distance for computing the closest distance point. You really only need to consider 4 points, which is the top, left, right, and bottom. So, we see the blue. The blue is the nearest point here because this is the top left corner. And then we can assume that the top left pixel in the original image is at 0, even when we multiply by 2, it's still at 0. The coordinate of the green is, in this case, at 1, 0. With respect to x, multiplied by 2 is 2, 0. So we have an issue here. This one's halfway between 2 colors. What do we do? Well, we can choose to do average, or we can always just pick a cardinal direction to always favor. So if we do this, we see we get a deep green, and then we can continue this out throughout the whole diagram. And we get a fairly interesting result.
You did not explain that well.
Well, we can choose to do average, or we can. This one's the coordinate of the green is.
Assume 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. At 12.
Is in this case at 1, 0. With respect to x, multiplied by 2 is 2, 0. So we have an issue here. This one's halfway between 2 colors.
How is this halfway between 2 colors? You don't make sense.
What do we do? Well, we can choose to do average, or we can always just pick a cardinal direction to always favor. So if we do this, we see we get a deep green, and then we can continue this out throughout the whole diagram. And we get a fairly interesting result. Bilinear interpolation. Please take special note of the name composition bilinear. So this algorithm works by iterating all points in the image. So for each pixel, we first compute the weighted average color with respect to the distance to the top left and top right. We actually do the exact same thing on the...
Fuck you. Oh my god, I hate these people. I'll just approximate it. Or I'll just abstract it. Huh? Every step in the expansive path consists of an upsampling of the feature map, followed by a 2x2 convolution, up convolution, that halves the number of feature channels and are concatenated with the... Yes, sir. I think I got it. I think I get it. Okay, but then that means that over here there's actually self dot down conv. I'll just call it half con. Half con. And then dot con 2D. Oh, this is should be input channels times 2, I think. That should be input channels. I think that's how it's done. Did I just zoom in again? No. X and then skip. Is that how they wrote it? What they wrote it as? I didn't say anything. Anyways, this is a 2x2 convolution with a stride of 2, I assume. Wait a minute. Wait a minute. No, it's not a stride of 2, it's just a 2x2 convolution. Per channel, and then kernel size 2, stride of 1. But 0. There should be times 2 3 1 1. Okay. 3 1 1. So just let me do the math real quick. With new, so let's say it's 16 minus 2 plus 0 plus 1. Blah. That makes 15. A stride of 2. How the fuck? How in the fuck? Alright, I'll do that. It's a little bit more, but it shouldn't be doing anything, right? 3. Gotta close my what's it called? My window. Okay, so I have my model now. What else do I have to do? I have my model. Now all I need to do is make the training loop, right? Right. So training algorithm. So I'll have let's have an epochs. Okay, you know what? I kind of want to delete this. This is not necessary. Okay, epochs. Let's have that up here. Epochs equals 200, like 1,000. I don't know. Actually, how does this go again? We do like a batch and do like steps and batches. Doing mini batch gradient descent. I forget how this works exactly. It's been a while. I'll just do batch gradient descent. So epochs 1,000 for I in range. Epochs. I'll just say for epoch in range epochs. Epoch. We will do. We'll need to sample x0. X0 equals. I forgot. I do forget. How does this work again? I gotta switch my chair. Alright, that's good. Move out of the way. Oh. All right. Okay, but again, I need to get my thing over here. My pillow. Okay. Need some lumbar support. Right. Test loader. I see, because the epoch goes across the entire training set. So for actually, you know what? Let me just print data loader. So these are already randomly shuffled, right? So that means I'll be doing this on a batch size of 128. I believe so. So I've already sampled my X0. Okay. I want a random T. Okay, this is the harder part. Well, actually, this might be extremely easy. That's supposed to tell me the that gives me the perturbed. So yeah, this is giving me the perturbed or the corrupted sample at time xt. Oh, okay. So this should be pretty simple. Noised. Actually, I already have the for diffusion. So noised samples equals alpha's comprod times images plus 1 square root 1 minus alpha's comprod times epsilon. Should be as easy as that, right? Oh, wait a minute. No. Okay, this is just for clarity's sake. Okay, so now I should do, all right, so model model equals unet predicted epsilon equals model noise samples and t. Oh shit! I need to do the I need to do the positional encoding. Oh, wait a minute, yeah.
Met Lucidchart maak je eenvoudige intelligente diagrammen en breng je je beste ideeën tot leven. Begin bij het begin of gebruik een schabloon. Geef je ideeën vorm met honderden vormbibliotheken.
A reverse sequence from t, which was 300 in this example, until 0, I iterate of stochastic events where each time step depends on the previous time step. A special property of diffusion models is that the latent states have the same dimensionality as the input. The task of the model can be described as. So now, after finishing the forward process, let's have a look at the neural network model in the backward process. The authors propose to use a UNet. This is a special neural network that has a structure that is similar to the one used in an autoencoder. UNets are a popular model for image segmentation, and their output has the same shape as the input. The input passes a series of convolutional and downsampling layers until a bottleneck is reached, and then the tensors are upsampled again and pass more convolutional layers. The input tensors get smaller but also deeper as more channels are added. Besides that, there are a lot of other components that are typically part of these UNets, such as residual connections between the layers, batch or group normalization, and also attention modules. As mentioned before, I aim to build a very simple and easy to understand model, and that's why I only use the main components of this architecture, such as down and upsampling, as well as some residual connections. One constraint of diffusion models is that the input needs to have the same dimension as the output. Because of that, the UNet is a great fit for image data. Our model will take a noisy image with 3 color channels as inputs and predict the noise in the image. Because the variance is set fixed, we will only output one value per pixel. That means the model learns the mean of the Gaussian distribution of the images. This is also called denoising score matching. Note that there were also experiments with predicting the image mean instead of the noise mean, and both approaches seem to work. One important thing is that we need to tell the model in which time step we are, because the model always uses the same shared weights for each input, no matter if it's 45 or 8. We will talk about this component in a second. The reverse process can also be formulated mathematically like this. We start in xt with Gaussian. This sample noise from the image xt during sampling. This is just a rough formula to give you an intuition. The exact one in the paper also considered shared parameters in our model. The neural network has shared parameters across time, which means it can't distinguish between the different time steps. That, however, means it needs to filter out the noise from images with very different noise intensities. To circumvent this, the authors used positional embeddings, which were presented in the transformer model. They are a clever way to encode discrete positional information like sequence steps. Positional embeddings can be visualized like that and have the task to assign a different vector to each index. For example, if you have the values 1, 5, and 10, the corresponding embeddings could look like this. The embeddings are typically calculated using sine and cosine functions for a specific embedding size defined by d in this case. For more details, I recommend to have a look at the Machine Learning Mastery blog post in the video description. The image with the code as simple as possible. That's
Bro. This should zoom in. Why are you zooming in? It zoomed in again, bro. It zoomed in again, bro. It zoomed in again, bro. It is 6 hours. Alright, I'm done sharing.